Okay, the last standard type of three-phase transformer connection is a delta primary and Y secondary. Again, this is made from 3 single-phase transformers with their primaries connected in delta and the secondaries connected in Y. One thing that's a bit different about this connection is it is the most common connection for three-phase distribution. In the field, utilities generally use a delta connection, and a Y secondary is the most common system that we use out in the field. And once again, we can see when we look at 3 single-phase transformers connected this way, the primaries are connected in delta, where I have a line connected to H1 of each single-phase transformer, and the end of each H winding is connected to the beginning of the next winding. End to beginning, end to beginning, end to beginning. On the secondary, again, we connect a line to each of the X1s of our single-phase transformers, and then the X2s are all connected together to bring out our neutral. And if we were to have 3 50 kVA transformers connected delta to Y, where the primary voltage is 600 volts and the ratio is 5:1, there are a number of questions we could answer for this. And I will just go through the primary ones here and just show you the question and the answer. I think they should be fairly straightforward. On the secondary, the phase voltage, in order to figure out that voltage, I need to know what the phase voltage is on the primary, because the ratio takes place from phase primary to phase secondary. With a delta connection, if the line voltage is 600 volts, the phase voltage will also be 600 volts. So that 600 volts divided by 5 should give me on the secondary a phase voltage of 120 volts. On a Y secondary, if the phase voltage is 120 volts, the line voltage should be 208. The rated secondary phase current would be, I could just use the rating of each phase on the secondary, which is 50 kVA, divided by the phase voltage, which is 120, and that would give me a secondary phase current of 416.7 amps. 50,000 divided by 120, 416.7. And once we have the phase current on a Y secondary, the line current is exactly the same. And another way to look at this delta Y connection is to connect a load on the secondary. In this case, we're connecting a 90 kVA balanced load at unity power factor on the secondary. And the secondary phase current, the easiest way to do it is just to use the mother of all power formulas and rearrange it. So if the formula is VA total equals V line times I line times √3, to solve it, to figure out the line current on the secondary, it would simply be the total VA divided by V line times √3. So 90 kVA divided by 208 volts times √3 is 208 amps. And if that is our line current on the secondary, with a Y secondary, if it's supplying that line current to the load, the phase current equals the line current, so the phase current would also be 250 amps. On the primary, we can say that the load connected on the secondary is reflected back on the primary and is like having that 90 kVA load connected to our V line of 600 volts. And to figure out the primary line current, again, we could use the mother of all power formulas. VA total is V line times I line times √3. Rearranging this formula, the line current would equal 90 kVA, our total load, divided by 600 volts times root 3, and gives us a line current on the primary of 86.6 amps. And for our delta primary, if the line current on the primary is 86.6 amps, the phase current is the line current divided by root 3, so 86.6 amps divided by root 3 is 50 amps. Hopefully, once again, this helps you to solve for values on these three-phase systems. That's it for now.